For this problem, we're asked to look at the equation of motion for the single degree of freedom system that is shown. There's a block of mass M connected back to ground with a spring of stiffness K. There's a dash pot at the bottom of damping coefficient C. And what we want to do is, one, know what the static deformation is of that block, and two, what's the undamped natural frequency and the damping ratio of the system. I'm going to say that X, by my definition here, is that X is equal to a 0 when the spring is unstretched. As it is shown there, it just says that X is measured positively down, but it doesn't say from where it's measured. So we're going to measure that from the position of the block when the spring is unstretched. So if I draw the position of the block at some state, we know that up here, this is the unstretched state. That displacement is X. So if the spring is unstretched, when X is a 0, it says that the force that's pulling back on this thing is simply K times X. There's going to be a weight force of mg, and then there's going to be a dash pot force. The dash pot force is going to have the magnitude of C times the magnitude of X dot. If X dot is plus, it means the block is moving down, which means that the dash pot is opposing that, and it's acting in the upward direction. So from our Newton equation, if we sum the forces, which is acting on the block in X, keep in mind that X is defined as being positive down, we got mg minus Cx dot minus Kx, and that's equal to ma, where A is equal to X double dot. So from this, our equation of motion, let me designate this as such. The equation of motion is mx double dot plus cx dot plus kx is equal to the weight mg. The static deformation, x static, is the deformation when system is in static equilibrium. That is, when it's in equilibrium, x dot is a 0 as well as x double dot. So we can see here that if we go back to this and we see mx double dot plus cx dot plus kx is equal to mg, static equilibrium means I cancel out this, and see that the x static is equal to the weight divided by g. The other things that we know is that if we take our equation of motion, if we divide through by m, we get x double dot plus c over m x dot plus omega, oops, don't want to write that down yet, plus k over m x is equal to g over m. Just g. Sorry. This we know by our definition is the undamped natural frequency squared. So omega n in this case is the square root of what number that you get when you divide k by m. K is given in the problem as well as m, and take the square root. This we know from our discussion in the lecture is that this is equal to 2 zeta omega n. So this 2 zeta omega n is equal to c over m. So the damping ratio here is c over 2 m omega n. Our undamped natural frequency is the square root of k over m. So we take the number for c that we know, divide by 2, divided by the square root of k times m, and it gives us that. So the task here was to derive the equation of motion for this. We start out with the free body diagram, where the block is acted upon by the spring, the dash pot, and weight. Newton's second law gives us our equation of motion. The static deformation in this case is just the weight divided by the stiffness of the spring. Our undamped natural frequency in this case is the square root of the stiffness of the spring divided by the mass, and the damping ratio is C divided by 2 square root of K times M.